Okay, so following on from last week where we were looking at basic integration methods and using that table of integrals, now we want to look at definite integrals. And the definite integral would be like this. For example, I'm integrating the function 1 minus 3x squared with respect to x between the limits 0 and 1. And that's how I'd write it notation-wise, putting the limits 0 and 1 on there. And this tells me the area under the curve between 0 and 1. So let's look at this function 1 minus 3x squared in autograph. Actually, I think I changed, didn't put 1 in, I put a different value in. 6 minus 3x squared. So let's just change that constant to a 6, please. Not that it really matters, but it fits in with what I'll put into autograph. Just a constant. 6 minus 3x squared. Now let's look at that on autograph. It's going to give me the area under the curve between those 2 points. So if I wanted to investigate it, I would type into autograph this function, and you'll be having a look at some of those tonight. So, fire up autograph and have a go at trying out some of these. So there's the function. Now, when we use integration in an engineering situation, and this is really why we want to do it, we're using it to model something that's going on, to try and mathematically represent what we're doing. And Daniel, we were talking about that. You had this resonant circuit, and you're going to come up with some function to describe it. So that's a mathematical model of the circuit. This could be the mathematical model of some projectile moving around and stuff like that. And what we need to do is to be able to understand the limitations. If we look at this, I'm finding the area under the curve, and this is the x value, so I'm integrating between 0 and 1. Let's go back to the function. I'm integrating with respect to x between 0 and 1, and that means I'm going to put the values of 0, x equals 0, and x equals 1 in, and that will give me the area underneath this curve between those 2 points. So let's go back to autograph. There's 0, and there's 1. And I could draw in the area underneath between 0 and 1. And it will tell me the area underneath that curve, which could well represent something useful. And we'll talk more about that later on. And you'll certainly, when you're doing your other modules, we'll be talking about what that area could represent. But mathematically, let's just get stuck into the process. Okay? So it could represent the area under the curve. But if you look at it, there are limitations. Look, at around about 1.4, then the area under the curve, if I then continue to try and plot it, is going to go negative. So it might have no sense in the situation that I'm talking about in this engineering situation. I might also not be interested in anything that goes on less than 0. So in other words, I have to make sure I understand the limitations of the curve and this model. I can only integrate realistically between 0 and about 1.4 to find the area of the curve. After that, if we expand out this curve, it will just drop very rapidly because it's an x squared function. So as x increases, it can get more and more negative, and the curve becomes more and more like a vertical descent. And so I could well only be interested in this small amount of area here. So I need to be aware of that, of the limitations. Let's just put this into our notes. And I'm going to put it into here. Yeah. So let's have a go at integrating this thing and then compare it to this curve here. So the limitations here are so we can usefully integrate between 0, well actually, if you are allowed to go negative, that's fine, negative about 1.34, something like that, and plus 1.3 or 4 by the looks of it, okay? Because the integral gives the area under the curve. So we can usefully integrate between minus 1 and plus 1.3, say, for this one, because the integral gives the area under the curve, and this function could be modelling an engineering situation where we're not interested in what happens when y goes negative. Plotting the function before we integrate helps us to see the limitations or the limits of our model, which is important. So how do we find this area? Do the integration and then put in the limits and take the bottom from the top, the bottom limit from the top limit. Let's see how that works in action. Okay, so I'm going to write the integration for this one. Integral between 1 and 0, 6 minus 3x squared. So do the integral. 6 becomes 6x. 3x squared becomes 3x cubed over 3. Tidy up, cancelling 3's, and we end up with this. Not forgetting to add this constant of integration at the end. Now, it's not right, so now we've done our integral, we're going to put the limits in, which is the second step in the process, remember. We've done the first bit, the integration, now we're going to put in the limits. So a little bit of notation. When we're doing this definite sort of integral, what we do is we put a square bracket around the integral when we've done it. And then we put our limits in, 0 and 1. So that's to tell me that this is a definite integral. I've done the integration now, 6x minus x cubed plus c. Now I'm going to put the limits in. And what that means is I substitute in the top limit first. So I'm going to rewrite this function, 6x minus x cubed plus c, but with x equal to 1. So, again, a bit of notation. I use these like curly brackets to signify that I'm putting the limits in. 6 times 1 minus 1 cubed plus c. So that's put the first limit in. And then I rewrite it, so again use the curly brackets, with the bottom limit in. 6 times 0 minus 0 cubed plus c.
Is that if you subtract?
No, I'm taking it away. So what we do is we take away, remember, the bottom limit from the top limit. So the top limit goes in and take away the function with the bottom limit in it. That's the process, and that's the notation that you use to do it. It's a pretty standard notation. Square brackets before you put the limits in, curly brackets to signify that you put the limits in. Now work out what these curly brackets are. So 6 times 1 is 6, 1 cubed is 1, so 6 minus 1 is 5, plus c, minus 6 nothings are nothing, minus nothing cubed is nothing, and c. So that's what I'm left with. 5 plus c minus c. And then, what is 5 plus c minus c? 5. The constant of integration always disappears because I'm doing c minus c every time. The constant of integration always disappears. So, when doing a definite integral, we don't bother to put it in. In other words, when I've done the original integration, I wouldn't have bothered to put the plus c at the end because I knew that when I put the limits in that form. Yeah, just leave the c out. So let's review this. What have I done? I have, how do you find the area under the curve? That's what we're finding, remember. Do the integration and then put in the limits. How do you do that? You do the integral as we've done last week. We put the c here, but we've seen now we didn't really need to bother, so it would have been quite perfectly okay to have left this square bracket as 6x minus x cubed, and then put it in, put the limits 1 and 0 outside. Then put the limits in and work out the answer. So what we found is actually that the area underneath this curve in this function here, the area here equals 5. In that example we have. And you might perfectly reasonably ask 5 what? 5 units. What unit we're talking about? That would depend on what x is measuring and what y is measuring. Okay? So when you do your electronics or you're looking at in mechanics or something like that, this could represent the distance, y could be a force, x could be a distance, in which case that would represent force times distance, because area is that times that. What's force times distance? Work done. Work is force times distance. And so on. So it all depends on the application you're putting it to. So what are the units for this area? It depends on what y is and what x is. But the area is 5. So if that would have been force in newtons against distance in meters, that area would be 5 newton meters or 5 joules, and it would represent the work done. So a useful thing to find, the area underneath the curve, has many applications. And that's the way we do it. Do the integration and then put the limits in. Okay. Let's look at another example. Yeah. Integrate this function between 4 and 2. So it's a definite integral. I know it's a definite integral because it's got limits in it. And I've plotted the function underneath. If we look at this function, when you've written it down, if you have written it down, have a look at this graph. This is a graph of the function. Does it make sense to you? Remember, on this horizontal axis is the x-axis, so that's representing x. As x gets smaller and we come this way, and we look at x in here, this, okay? So as x gets smaller, what happens to x squared? It gets smaller, yeah. Until in the limit, when x is 0, what's the value of 3 over 0? No, infinite. It's an infinite number. How many zeros can I get out of 3? As many as I like. Okay. So actually, as x approaches 0, y approaches infinity. So that's a definite limitation in this model. There's no point in putting the limit of 0 in here because that's an infinite number. So that's an instant limitation on this model. 0 cannot appear as one of the elements. You can see why now, because at 0, the area under the curve is infinite. So if I did put the 0 in here, I'd get an infinite answer for the area under the curve, which wouldn't really make any sense. So what I want to do now, anyway, is just to have a look at this and find the area under the curve between 2 and 4. So where is 2 and 4? There's 2 and there's 4. So I'm finding the area under the curve between there and there. And that might well represent something useful depending on what's on the y-axis and what's on the x-axis. So let's go through the process. Integrate between 4 and 3. What was it? 4 and 2. Thank you. 3 over x squared dx. First step, do the integral. From last week, how would I have to rewrite 3 over x squared to be able to do this integration? Using those indices. Integral between 4, 3, x to the minus 2, right, dx. Because the inverse means a minus power. So I would rewrite it like that. And then perform the integration. Add 1 to the power, divide by the new power. X to the minus 1 divided by minus 1. This time we're not going to bother to put the c on because it's a definite integral. So what I do instead is put the square brackets round it and put my limits in, 4 and 2. Now, it probably is easier to think of this as not x to the minus 1, but to remember that x to the minus 1 means the inverse. So let's rewrite that as minus, because the whole thing's negative, that's what the minus 1 underneath is telling me, 3 over x, between the limits of 2 and 4. Have a look, just check that makes sense, that step from there to there. Okay, now the next step, we've done the integral, we've written it in a convenient form, minus 3 over x. The next step is to put the limits in. So we revert to the curly brackets, minus 3 over, put the top limit in first, minus, and then we put the bottom limit, minus 3 over 2. And then we work out the answer. Minus 3/4 minus 3 over 2 is plus 3 over 2. We don't need to do it through a calculator because all I've got to do is make the denominator the same. Minus 3/4 plus 6/4 is 3/4. So the area is 3/4, positive 3/4. Which is just as well, because if we think back to the curve that we drew, we had a positive area underneath here. So if we hadn't had a positive answer, I'd have been wondering why. So the area underneath here is 3/4. Yeah. So, look back at this solution. Minus 3 over x, remember, is our integral. And think back to the function. Well, we were talking about the fact that when x equals 0, there was no sense in the solution. Because at 0, y approaches infinity. If you look at our answer, which was minus 3 over x between 4 and 2, in other words, here, you look at this. If x is 0, then we must get an infinite answer. Negative 3 divided by 0 is an infinite answer. If you try to do that on a calculator, you get a math error. It won't do it. Okay? So that shows the limitations. However, what happens if I do this? The integral between minus 2 and 2 of 3 over x squared dx. Let's go through this integral. I'd like you to do it. Now let's put minus 1 and 2. Follow the steps that we've just done and work out that solution. Okay? So we have negative 3 over x, that's the integral between the limits 2 and minus 1. If I put them in, I get negative 3 over 2 minus negative 3 over negative 1, which is negative 3 over 2 plus 3, which is 1.5. Sorry, minus 4.5. Okay, correction. Recording here. So why are the 4 exclamation marks there? If we look back at the original function here and here, there's no such thing as a negative area. But mathematically, it's given us an answer. And to compound the impossibility of it, between minus 1 or minus 2, whichever it was, and 1, but in other words, right, between minus 1 and 2, we've gone through an infinity, effectively. And so this is an example where you've got to be very careful that the mathematically we can work out what that integration is, no problem. But we can easily miss, unless we're careful that we apply the model correctly and look at the function before we do the integration, we can easily miss something like this and come up with an answer that actually makes no sense in the real world. And that can lead us down a false path. So, just to make a note on that, mathematically, we get a solution however, looking at the function, we can see that this makes no real sense. It's important to check the limitations. Of a model by looking at the function. Plotting the function, looking at the function, whether we use software to plot it or we just plot a graph, it's important to have an idea what the function looks like, rather than just blindly go ahead and put our limits into the integral, because it might not make any sense. That's a completely nonsensical solution, minus 4.5, for two reasons. We can't have a negative area, and we've got this infinite value in between when it drops to 0. Okay, let's have a look at another example. Integrate that sine function between pi by 3 and pi by 2.
Minus 1 and 3.
Okay, have a go at the integral. So what's the integral between pi by 3 and pi by 4, pi by 2 rather, of this integral, 4 sine 3x. Write down what you think the answer is. Hopefully you got sine becomes minus cosine, and the 3 comes out and goes underneath. So you get minus 4 over 3 cosine 3x between the limits pi by 3 and pi by 4. I mean pi by 2. There is a problem here when we come to put the limits in. Let's have a look at the function. Do you remember what we were saying on the previous slide? How important it is to look at the function and check what's going on. And this is, Ethan, what you were talking about earlier, in a way. If we look back at this, and this function here, this point is pi by 2. It's not very clear, but this is pi by 2. And this, therefore, must be pi by 4. And I want to integrate between pi by 2 and pi by 3. So I need to find out where that is on here, because if it is this side, then we're going to have to take into account the fact that some of the area is above it. If it's this side, then we're okay, because the area is all then below and we've got negative. So we need to find out what is this point here. What is this point at which the sine, which is what the y-axis is telling us, at which point at which 4 sine 3x drops to 0. So we need to do a little bit of a side calculation first to check that point. We need to find, before proceeding, find the point at which 4 sine 3x equals 0. Which is reasonably straightforward to do. If I divide both sides by 4, 0 divided by 4 is still 0, so sine 3x must equal 0. So I'm after the angle whose sine is 0. Okay? Sine to the minus 1 of 0 will equal 3x. The sine whose angle is 0 is 3x. Okay, I'm getting myself in a bit of a muddle here. The sine of 3x is 0. So what angle gives 0? It will be 0, won't it? Yeah, it will be 0, but also other angles. Oh dear. Right. I might have to rethink this, because I've introduced, and I didn't intend to introduce this idea of adding extra angles, and I'm going to overcomplicate it. So let's come back to that question. Okay. So I do want to talk about the idea above and below, but I thought that would be a nice way to do it. However, it's introduced something else. I don't want it at this point. So let's just hold our fire on that particular problem, finding out where this point here is, and come back to it, okay? So just give yourself room to finish this question off, and yeah, will be fine. And then we'll come back and have a look at it, okay? Put that on one side for a minute, because I want to give you some work to do actually, and if we carry on with that, we'll be here all night. So let's look at one more, okay? And I'll let you have a go at this one. It's an exponential function, and I want to find the area under this curve between 0 and 1. 0 is okay in this model, because it's not disappearing off to infinity at 0, and 1 is here. So those are the 2 points I'm interested in. So I'm after this area. So that's okay. I'm not going through in any infinities here. It's perfectly valid to find the area between 0 and 1 for this function. So have to hand your table of integrals, so you can remember how to integrate that exponential function there. Integrate and then put the limits of 1 and 0 in and work out that area underneath the curve. Hopefully you got that as the integral. 5 over 3 e to the 3x. Now all we need to do is put in the limits and work out what it is. You may well have done this, however, before proceeding from here, if you've not quite got that far yet, whenever we have inside the integral, at this point here, before we put the limits in, if there's any constant inside the square brackets, if you think about it, we're going to multiply that 5 over 3 by this exponential function when x equals 1, and then again when x equals 0. So it can come outside the bracket, which sometimes or can make life much easier for you. So at this stage, I would write this. No, I wouldn't. I would write 5 over 3 square bracket e to the 3x between 0 and 1. And then I'd put my limits in, but I'd put them all inside a square bracket and put the 5 over 3 outside. And then at the very end, just multiply by 5 over 3. It just makes the calculation a little bit quicker.
We don't get the same answer.
Yes, you would get exactly the same answer, so don't worry if you've not. So I'm going to put e to the 3 times 1 in the first curly bracket minus e to the 3 times 0 in the second curly bracket. But then once I've worked that out, I'm going to multiply the whole lot by 5 over 3. E to the 3 minus anything to the power 0 is 1. So I end up with that. And then I work it out on the calculator. And I get, and you should get 31.8, okay, is your area underneath the curve. Okay, so right, I have one more example for us to look at, but I'm going to skip past this one reasonably quickly. If you want to have a look at it in more detail, you can make a note of it, but you can look at the video afterwards. If you have a look at this function 4 over 3x, and we look at the function, then you can see this is another example where you've got to be very careful with the limits. Because again, and it's often any sort of inverse is going to have this problem associated with it. At 0, the thing shoots off to infinity. So that's one very big limit to this thing. And we could easily fall into the trap of integrating negatively and positively and coming up with some sort of answer that really doesn't make any sense. So that's another example of a function. Well, don't include infinity, yeah. In an inverse case, you can't have a So what I want to do now, though, is to just point you at this exercise, which is in your textbook. It's the further problems on definite integrals on that chapter on standard integration. I'll write up here in a minute what the page number is in the new textbook. But here it is. And after the break, we're going to have a break now, I want you to log on to Autograph, have a go at these questions in here, work out what the definite integral is, but just plot the function. It doesn't ask you to do this in the exercise, but what I would like to do is to look for any limitations of the model. At what points could you not find the integral between? And then write those down. Okay, just investigate these functions at the same time as you're doing the integration to check that you can do it. Okay?